Some people might think, yeah, there is this problem with infinity. I don't think it's a problem with infinity per se. I think it's a problem with the way we think about infinity. Whenever a mathematician stops cranking through the equations and starts thinking about, how should I understand this? Why are things working like this? They're starting to do philosophy. And whenever a philosopher starts thinking about, how do I tease through the consequences of this? What follows from this? She's doing a bit of mathematics, she's doing a bit of logic. The area in which philosophy and mathematics intersect, for me, is one of the most fascinating ones, but it's also one of the hardest, especially when you've got infinity in there.
In early 2012, I posted on existix101.com what has become a controversial document, C3, the Canonized Cardinal Continuum. It's a modified version of an essay I wrote as an undergrad while studying logic and the development of the calculus, as part of a special projects course I took while getting my bachelor's degree in philosophy. It didn't take long to draw unwanted attention. There's a lot of mathematical crackpottery out there. Most of it is just pointless and dull. After you eliminate that, you get realms of insanity. After you eliminate that, sometimes, if you're really lucky, you'll come across something truly special, where someone has created something so bizarre, so overwrought, so utterly ridiculous that it is a masterpiece of insane, delusional foolishness. Today, we have an example of that, Existix. This is a body of work by a high school dropout named Gavin, Wince, with truly immense delusions of grandeur, pomposity on a truly epic scale. Wow, it's pretty hard to get such a nasty review, especially the part stating I'm a high school dropout, despite having both my bachelor's and master's degree diplomas posted on my website.
Our story starts here, at the town's university, with a mathematics professor, a man called Georg Cantor, who started a revolution he never really meant to start, but which eventually threatened to shake the whole of mathematics and science on its foundations. By asking himself a simple question: how big is infinity?
The first modern thinker to confront the infinite was Galileo. And he tried to do it using the circle. This is how he did it. He said, first of all, draw a circle. Now put a triangle inside it, then a square, and keep on going, keep adding sides. Eventually you realize that what the circle is a shape with infinitely many, infinitesimally small sides. But as soon as he'd done that, he realized it actually opened up a horrible illogical paradox. Let's draw a bigger circle outside. And now, with an infinitely sharp pencil, draw from the center infinitely sharp lines, one for each of the lines on the inner circle. All right, there's an infinite number of them. That should be enough for the inner circle. But now extend those lines out till they meet the outer circle. Now those lines are diverging, which means when you get to the outer circle, if you look really carefully, there will be gaps. There won't be enough. And Galileo just said that makes no sense. So let's use the concept if we must, but let's not try and understand infinity. And that's exactly how they left it, until Georg Cantor came along. Cantor found he could add and subtract infinities, and in fact discovered there was a vast new mathematics of the infinite. He's already grasped and understood the nature of real infinity, which no one before him had done. But then that same year he comes up here to the Alps to meet the only other man who really understood his work, a mathematician called Richard Dedekind. Within a year of their meeting, he announces an astonishing discovery. He already knew that when you looked at the number line, it divided up into an infinite number of whole numbers and fractions. As he looked closer at this line, that infinite though the fractions are, each one is separated from the next by a wilderness of other numbers, irrational numbers like pi, which require an infinite number of decimal places just to define them. Against all logic, the infinity of these numbers was unmeasurably, uncountably larger than the first. What had frightened Galileo, Cantor had proved. There was a larger infinity.
One of my philosophy professors recommended I take a class he was offering, covering the development of the calculus and set theory.
Set theory is the study of sets. A set is basically a group of things. Sets are also all sorts of different things. You can even have the empty set, which is a set that contains nothing. You can even have sets that include themselves, such as the set of all sets that are listed here.
This was the first time I was exposed to Cantor's continuum hypothesis. I began to modify some of my own mathematics to satisfy aspects of Cantor's work and vice versa.
What was inspiring for Cantor frightened his critics. They saw mathematics as the pursuit of clarity and certainty. Everything Cantor was doing, his irrational numbers and his illogical infinities, seemed to them to be eating away at certainty. He soon faced a deep and implacable hostility. Other mathematicians actually tried to prevent Cantor publishing his papers. And he was also attacked personally. The great mathematician Henri Poincaré said that Cantor's mathematics was a sickness from which one day maths would recover. And worse, his one-time friend and teacher, Kronecker, said that Cantor was a corrupter of youth.
Little did I know that this was academic heresy, worthy of being ostracized. Two individuals have written reviews of the C3 essay in some detail. Alexei Avenchenko of kalikanzarid.blog.ru, graduate student studying analysis at Kemerovo State University, and Mark Chu Carroll of Scientopia.org, software engineer extraordinaire, former research staff member at IBM, senior software engineer at Google, currently staff engineer at Twitter. Not your everyday critics. Obviously, these guys know mathematics. Both claim that Mr. Wince believes that he has solved the continuum hypothesis. I make no such claim. Rather, I point out the utility of C3 extends beyond the continuum hypothesis to infinitesimal calculus and non-standard analysis seamlessly. This may be a bold statement, but a bold statement about infinitesimal calculus and non-standard analysis, not the continuum hypothesis. The words continuum hypothesis only appear twice in the C3 essay, whereas non-standard analysis appears 48 times. If anything, I'm attempting to further the work of Edwin Hewitt or Abraham Robinson, rather than furthering the works of Kurt Gödel and Paul Cohen. Contemporary set theory doesn't have a monopoly on the concept of infinity.
Well, infinity was always there, but they tried to contain it. They tried to keep it in a cage. People would talk about potential infinity, not as opposed to actual infinity, but Cantor just goes all the way. He just goes totally berserk. And then you find that you have infinities and bigger infinities and even bigger infinities, and for any infinite series of infinities, there are infinities that bigger than all of them. You know, infinity is so big that you can't even give them names. This is it's just fantastic stuff. And people got frightened. They've emasculated set theory. They have this version which is safe, called Zermelo-Fraenkel set theory, which is a sort of a watered down. But you see, that takes all the fun out of it.
Robinson was a big fan of Gottfried Leibniz, progenitor of infinitesimal calculus. So am I. There, that's not me in drag. I'm dressed up as Leibniz in another video. Look, Leibniz is being exhumed from the grave, philosophically, in some other video I made. See what I mean? Mark CC says, the continuum hypothesis is a question about the cardinality of the set of real numbers and the set of natural numbers. Neither infinites nor infinitesimals are part of either set. Which is real funny, pun intended. However, if we look at page 36 under the section titled C3 and the conventional approach, the infinitesimals and infinites are hyperreal and transfinite numbers. If the continuum hypothesis has been proven to be improvable, which I'm not going to argue with, and all I've done is post an essay dealing with some experimental mathematics. What's the big fuss all about?
A lot of people have been asking me the same question recently. It obviously bothers a lot of people, so we need to get this sorted out. Why does 0.999 recurring equal 1? And I remember asking my maths teacher this myself when I was at school.
On one occasion, it was suggested by one of my professors that if I wanted my infinitesimal mathematics to be successful, I should devise a Dedekind cut-like process to demonstrate infinitesimals on the continuum.
This is one of the great ideas in mathematics that's due to Dedekind, and it was a definition of real numbers in terms of rational numbers. There are a lot of rational numbers, but there are also lots of holes, as we've seen. And Dedekind had the idea that what a real number really is a way of dividing the rational numbers into two parts. Let's say this is going to be a real number, A. Then Dedekind said that what A really is the set of rational numbers less than A together with the set of rational numbers greater than A. So these two sets tell where A is in the real numbers. So I've defined holes out of existence this way. This is the sort of thing that people study in maybe the junior year course in mathematics.
Or philosophy, by the sound.
Or philosophy. These are called Dedekind cuts.
For starters, I decided to use basic algebraic rules applied to the assumption that 0.9 repeating does not equal 1. This would allow me to produce some infinitesimal number that, when added to 0.9 repeating, equals 1.
Who knows what waits for us in nature's no man's land?
Impossible, unbelievable, but I tell you it could happen. It could happen. It could happen. It could happen.
First of all, the universe is not going to collapse in on itself just because we experiment a little with mathematics. Even though it is known that experimenting with mathematics can lead to harmful side effects.
After his breakdown, everything about Cantor is transformed. He never stops working on the continuum hypothesis. It's as if he just can't put it down, can't look away. Gödel, like Cantor before him, could neither solve the problem nor put it down, even as it made him unwell.
But seriously, let's review the controversy surrounding 0.9 repeating being a decimal representation of the number 1.
99.9 repeating % of mathematicians agree. 0.9 repeating equals 1.
When we write numbers decimally, sometimes we have more than one way to write the same number. So 0.999 recurring is just another way to write the number 1.
So it's an issue of notation, as Mark CC points out. I have no problem with that. I agree. The conventional argument works. 0.9 repeating is just a decimal representation of 1. However, I can imagine the alternative argument, that 0.9 repeating does not equal 1, and use the same exact reasoning, given that this is just an issue of notation.
0.9 repeating is a decimal number, a real number. See, if you want 0.9 repeating to be that number infinitesimally close to 1 but not 1, and let's face it, some of you do, then you're writing down the wrong number when you write 0.9 repeating. That number, infinitely close to 1 but less than 1, is a number, but it's not 0.9 repeating, or any real number.
Nothing about the use of symbols or notation prevents someone from changing rules slightly to see what happens with a different set of rules.
Mathematics is about making up rules and seeing what happens, and it takes great creativity to come up with good rules. If you don't follow your invented rules precisely in mathematics, people have a tendency to tell you you're wrong. Some rules give you elementary algebra and real numbers, and these rules can't tell the difference between 0.9 repeating and 1, just like they can't tell the difference between 0.5 and a half.
The algebraic rules that work well with assuming 0.9 repeating equals 1 can also work with the assumption 0.9 repeating does not equal 1, given a few exceptions that require redefinition.
If 0.9 repeating and 1 were different real numbers, there would have to be infinite other real numbers between them.
If you want, you could say s equals 0.999 recurring, and then say, times it by 10. 10s equals 9.999 recurring. Take the difference, and you'll get 9s equals to 9, and obviously then s equals 1. So you've got s equals 0.999 recurring, and s equals to 1. Now that isn't a mistake. What we've shown here is that there are two ways to write down the same number.
Last week I made a video listing 10 reasons 0.9 repeating is 1. I have now collected proof that every single one of these reasons is invalid. First, let's look at the so-called algebraic proof. It starts by saying 0.9 repeating equals x. This is already wrong, because later it turns out that x equals 1, and if x is 1, then that means 0.9 repeating equals 1 right in the beginning. You can't assume stuff before you prove it.
With these examples, there are two answers. If we assume 0.9 repeating does not equal 1. You might think that treating these as two different answers is pushing towards contradiction. However, just as 0.9 repeating equals 1 can be used in standard mathematics, 0.9 repeating not equaling 1 can be used for non-standard mathematics.
Well, go to college and learn about hyperreals, or better yet, surreals. That's a system where you can have a number that's infinitely close to 1 but not 1, but even weirder, there's infinity more numbers that are infinitely even closer.
For me, the fun of the Cantor was that he was playing on the edge. You know, the idea was you had these ideas, they sounded great, but they were very dangerous.
So let's take 1 minus 0.999 recurring. Then you could think of it as a string of zeros, 0.0000, going on forever. And it does go on forever. There is no number at the end of that. There is no pot of gold at the end of that rainbow.
But you might be tempted to think there's some sort of final one beyond infinity. Let's write that down as 0.0 repeating 1. Of course, if the 0 repeats infinitely, then you never get to the 1, so you might as well leave it off the number. Thus, the difference between 0.9 repeating and 1 is 0. There is no difference.
In other words, it's 0. Technically, we say it's infinitesimally small, but that's 0 for us.
By using 0.9 repeating symbolically to represent a hypothetical number, infinitesimally less than 1, we have done nothing more exotic than had we used the letter X to represent the same. We could have used a silhouette of Chuck Norris for that matter. It makes no difference. It's just notation, remember? The only issue is that if we are to treat 0.9 repeating differently, then we need to be prepared to treat several other notations differently, such as 1/3 equaling 0.3 repeating, and so on.
0.3 repeating plus 0.3 repeating plus 0.3 repeating isn't 1 because it's missing the 0.0 repeating 1. That's the difference between 0.9 repeating and 1. For these to actually each be 1/3, you have to split the 0.0 repeating 1 between them. And 0.0 repeating 1 divided by 3 is 0.0 repeating 3, 3, 3, 3, 3 repeating, and then after infinity, more 3's repeating. Except that adds up to 0.9 repeating, and so on. So it's not enough to have 3's to infinity. They have to go to, like, super infinity. They will probably kill me if I don't say April Fools.
It's not that this cannot be done. It's that it either hasn't, or it's not considered useful. However, this doesn't necessarily mean that these symbols cannot be used with a different set of rules. Notice Alexei states, in his critique of my partial sum series, "There's nothing wrong with this, except that one needs to be extra careful when reasoning with infinite ordinals." Alexei then argues, 0.9 repeating equals 1 unless some alternative to these use of real numbers is introduced. If we adopt some model of real numbers which admits infinitesimals, we never actually reach 1 while summing the series. You mean 0.9 repeating would not equal 1? Now that's funny. 0.9 repeating has a strange attribute, the ... part, which represents an infinite sequence of decimal places. We can argue that 0.9 repeating has a unique and distinct identity separate from 1. This is used to initiate establishing the existence of some infinitesimal, a very loose definition initially, to be tightened up as we go further along. The basic idea for an infinitesimal, a number infinitely small and greater than 0, is inconsistent. For every infinitesimal number, there is an even smaller number greater than 0 that can be imagined ad infinitum. Mark C.C. states, "Infinitesimals are not real numbers. You can't reason about them as if they were members of the set of real numbers, because they aren't. Many of Wince's mistakes are based on this idea." Again, referencing to page 36, infinitesimals are treated in C3 as hyperreal numbers, not real numbers, as Mark C.C. continues to misrepresent. Interestingly, Wikipedia states, "Cantor was paradoxically opposed to theories of infinitesimals of his contemporaries, describing them both as an abomination and a cholera bacteria of mathematics." To demonstrate the importance of rigor, Alexei sets forth 2 postulates with 2 proofs to show there is no least possible value greater than 0. The rigor Alexei uses to demonstrate there is no least possible value greater than 0 is not overlooked in C3. It states, "To avoid the regular arguments which dismiss the consistency of the concept of infinitesimals in mathematics, we will assume that K is a set of infinitesimals such that any conceived quantity smaller than K and greater than 0 is a member and/or subset of K." Is it a problem that I did not express C3 in terms of formalized mathematical logic? Alexei's first proposition is an oversimplification of a complex issue, which my unconventional notation attempts to express. When introducing new concepts that go outside the norm, informality shouldn't be the primary criticism. Also, Alexei's postulates and proofs demonstrate a type of naive set theory which, as rigorous as it might be, succumbs to Russell's paradox.
This theory says that the problem with kind of naive set theory is the naive comprehension principle. There exists some set A, such that for all x, x is a member of A if and only if condition phi applies. Let phi be x is not a member of itself. If A is a member of A, then condition phi does not apply and A is not a member of A. If A is not a member of A, then phi does apply and A is in fact a member of A, and we're stuck in a loop, we're stuck in the paradox. And this is why it's a problem for this kind of basic naive comprehension principle.
Experimenting with the basic rules of algebra and hyperreal numbers gives very interesting results, which may not be fully captured within a contemporary set theoretical axiomization. If we re-examine the proofs to Alexei's first postulate, substituting k for x, according to C3, 1/2 k is no less in degree of infinitesimal than k, so 1/2 k equals k. If we apply this concept to Alexei's proof for his first proposition, k is less than or equal to 0, which is consistent with C3. Mark C.C. states, "Infinitesimals are fascinating. You can reconstruct differential and integral calculus without using limits by building in terms of infinitesimals." Interesting statement. Didn't Mark C.C. read the table of contexts? Somehow Mark C.C. didn't notice that the essay he was reviewing was centered around reconstructing differential and integral calculus in terms of infinitesimals.
Infinitesimal quantities show up in the history of mathematics, including 2 of our favorites, Newton and Leibniz. Newton referred to them as fluxions, and Leibniz referred to them as differentials, and he wrote them as these little quantities that we're already familiar with. So the notation that we use comes from Leibniz. Now, Newton and Leibniz were not doing limits. Newton and Leibniz had an intuitive understanding of how to use them. The philosopher George Berkeley was highly opposed to the use of these quantities, and in 1734 he published a work called The Analyst. And in this work he attacked what he referred to as an infidel mathematician, presumed to be Newton. And he didn't just attack the mathematician, he attacked the mathematics itself. Berkeley would say that Newton and Leibniz would present calculus something like this. F of x is x squared. So the calculation of the derivative would be this. And so let's put in x squared here into this function. So the derivative would look like this. And let's work that out. We get, and then you can see this x squared and the minus x squared cancel out. And then we can cancel out a dx. And then we get 2x plus dx. And we can ignore this dx because it is infinitely small, so we can just strike it out and we get the derivative is 2x. Then Berkeley would say this, aha, look here. First, you're treating dx as a non-zero quantity. Whenever you have it in the denominator here, it's not zero. And then right here, you're ignoring it as if it is zero, and you can't have it both ways. There's a contradiction there. That's the type of thinking that led to the formulation of the theory of limits. Augustin Cauchy and then Weierstrass, they reformulated the development of calculus in terms of limits. So they would have said delta x is just approaching zero, it never quite gets there, so we don't have the problem of dividing by zero. But consider the fact that if you bring it on up to the 1960s and look at the work of people like Abraham Robinson, Robinson did what is commonly referred to as non-standard analysis, with the standard analysis being the approach dealing with the theory of limits. And Robinson was doing math with infinitely small numbers, dx and dy, and the reciprocals of those numbers, which would be infinitely large. And he expanded the set of numbers beyond the real numbers and included what we would call hyperreal numbers. Those would be these infinitely small and infinitely large numbers. Robinson showed in a rigorous fashion, using these concepts of hyperreal numbers, that the intuitive understanding of dx and dy as infinitely small numbers but not quite zero that Newton and Leibniz had is mathematically and formally correct. And in fact, Robinson said that his goal in studying all of this was to get inside Leibniz's head and to thoroughly understand his thinking.
Section 1.2, Degrees of Infinity, draws attention to the fact that the term 1 over 2 to the power of n, used to deduce some infinitesimal, conveniently, is the inverse of the term used for deriving power sets, 2 to the power of n. Alexei states, if n is a number, then 2 to the power of n is also a number. Treating n as a set without assuming any concrete set theoretical model of arithmetic is a recipe for disaster. At the beginning of page 10, Wince substitutes aleph for infinity. This is an unfortunately common mistake among the beginners. Cardinal numbers and the infinity encountered in analysis are completely different notions. There is no connection between these notions unless you can explicitly and rigorously establish one. Infinity represents boundlessness, limitlessness. This is not a number. However, aleph naught and aleph 1 are two distinct cardinal numbers representing sets with infinite elements, where aleph naught is the infinite set of countable numbers, and aleph 1 is the infinite set of uncountable numbers. The distinct cardinality between these two aleph numbers raises this question. If, for every infinitesimal, a smaller infinitesimal can be imagined, and we know of at least 2 degrees of infinity, why can't we treat infinitesimals as a special set and degrees of infinity as some other special set, such that both sets represent a special reciprocal relationship between infinites and infinitesimals? As far out as this may be, it is hardly ridiculous. Both critics laser focus on issues, which can suck people into lengthy debates over technicalities that for the most part are dealt with throughout the C3 essay. Neither appreciate that the C3 essay starts with very undeveloped ideas that progressively conform to more strict rules. For example, Mark CC states, "There's no such thing as an infinite root. Roots and exponents aren't defined for infinity because infinity isn't a number." However, if you examine section 1.4, roots of infinites and infinitesimals, and section 1.5, arithmetical treatments of infinites and infinitesimals, we define roots and exponents to handle infinites and infinitesimals. Section 1.4 lays out the relationship between hypothetical extra-finite quantities that intermediate between the finites and the infinites, and between the finites and the infinitesimals. The same reciprocal relationship that exists between infinites and infinitesimals is extended to alpha and omega. Further, alpha and omega are both sets where alpha is the set of all roots for infinitesimals, and omega is the set of all roots for infinites. For this case, alpha and omega are parameterized between k0, the initial infinitesimal, and alpha naught, the initial infinite. In section 1.5, a series of increasing square roots and a graphic representation of exponential curves are examined. They both demonstrate that the treatment of infinites and infinitesimals as exponents is compatible with the treatment of real numbers. It can be hypothesized that any finite quantity greater than 1 raised to the infinitesimal root equals 1 plus some infinitesimal. Unfortunately, Wince doesn't prove this properly or refer to any existing proof, instead relying on a heuristic argument, says Alexei. So what? Words like hypothesize imply deduction. The deduction theorem applies generally to the reasoning of C3. Formalizing C3 into mathematical logic would be part of a cleaning up process for modern logic and mathematical practice. Something for a dissertation, perhaps. Alexei states, Wince then proceeds to state the continuum hypothesis incorrectly. However, if we look at the C3 essay itself, we can see that it is not stating the continuum hypothesis at all. Though what I am doing resembles the continuum hypothesis, it is not the same thing. Referring to the Stanford Encyclopedia of Philosophy under the continuum hypothesis, section 1.1, regular cardinals, it states, "There is no mystery about the size of 2 to the power of n for finite numbers. The first natural question, then, is whether 2 to the power of aleph naught is located in the aleph hierarchy. Is it aleph 1, aleph 2, aleph 17, or something much larger? The cardinal 2 to the aleph naught is important since it is the size of the continuum, the set of real numbers. Cantor's famous continuum hypothesis is the statement that 2 to the power of aleph naught is aleph 1. Paul Cohen states that mathematicians may eventually come to accept that the continuum hypothesis is obviously false. We feel it absurd to think that the process of adding only one set at a time can exhaust the entire universe. Now aleph 1 is the cardinality of the set of countable ordinals, and this merely a special and the simplest way of generating a higher cardinal. The set C, the continuum, is, in contrast, generated by a totally new and more powerful principle, namely power set axiom. Thus C is greater than aleph sub n, aleph sub omega, aleph sub alpha, etc. This point of view regards C as an incredibly rich set which can never be approached by any piecemeal process construction. Therefore, it is free of contradiction to assume that the continuum and the set of all real numbers are not the same set. at the top of page 7. It's explicit that we are assuming Aleph 1 does not equal the continuum, and that Aleph 1 is less in degree of infinity than C. That the set of all real numbers has a smaller cardinality than the continuum. In other words, we are assuming C does not equal Aleph 1, which commits me to a cardinal continuum with infinite degrees of infinity leading toward what would then be equivalent to C. Avoiding the set of all sets paradox becomes an imminent issue. Alexei doesn't mention this. Rather, he states, Mr. Wince makes another mistake, ignoring the obvious fact that 2 to the power of C is greater than C, which we obtain by applying the theorem of power sets discussed above about C. One could imagine some power set where 2 to the power of C is greater than C, such as generating the third Beth number. However, it could be argued that this C is not really the continuum, and any series of Beth numbers are not really greater than any Aleph numbers. It's just a form of relabeling. In C3, the continuum is treated in such a way that the power set of C is meaningless. Alexei states, the definition Aleph naught raised to the power of Aleph naught equals Aleph 1 is inconsistent with the standard definition of Aleph 1. 2 things. I'm using the Aleph notation to denote known distinctions between infinite sets, and I have expanded the continuum to include hyperreal transfinite numbers. The C3 treatment of these distinct cardinal numbers is not inconsistent with the standard definition. C3 adds to the definition, not to confuse Aleph numbers with infinity, not to confuse real numbers with cardinality, nor to incorrectly misuse or define symbols. For every algebraic rule applied to these infinites and infinitesimals, the more there is a commitment to consequences that result. I did not pull these mathematical equalities out of a hat. These expressions are deduced by applying algebraic rules to the initial assumptions, lead where it may. Mark CC states, for example, on his way to proving that infinitesimals have this range property he calls perambulation, he defines a value that he calls k. Actually, no. This is not the definition of k. K is defined in section 1.3 on page 9, where it states, let k be substituted for this infinitesimal quantity, such that k equals some infinitesimal. K is initially defined arbitrarily as some infinitesimal. Mark CC has taken something out of context, which doesn't appear until section 1.5, unfairly making C3 look wildly speculative. If we go back to the graphic representation of exponential curves, we see an interesting pattern. For any given function of x, where x is an exponential, when 0 is an exponent, y equals 1. This is not radical. This is very ordinary. Yet, if we zoom in and look closely at the function of x, where x almost equals 0, it can be hypothesized that any finite quantity greater than 1 raised to the infinitesimal root equals 1 plus some infinitesimal. Mark CC states, Mr. Cringe doesn't let himself be limited by silly notions of consistency. No, he defined things his own way and runs with it. Actually, Mark CC ignores how these symbols are being used, ascribes his own meaning to these symbols, and takes statements out of context. It's no wonder his review is full of confusion and misunderstanding. Mark CC states, Wince has got a very strange idea that infinites and infinitesimals don't have fixed values, but that their values cover a range. The way he gets to this idea, by asserting the existence of infinity as a specific numeric value and then using it in algebraic manipulations. Alexei states, somehow, Wince arrives at 3 solutions to an equation, 3 results of applying previously defined rules to a single expression. Let's have a look at perambulation and see what it says for itself. In section 1.6, range of values, though not proven, we have justified examining this expression. Part of the justification comes from what we already know about exponentiation. It's reasonable to assume that any real number raised to the power of some infinitesimal equals 1 in some infinitesimal. Whether or not this can immediately be proven, it has consistency. After substituting infinity with an Aleph number, we can attempt to factor this equation. Alexei states, Wince's factoring makes no rational sense, so I won't even try to explain it. In the middle of page 14, we see ordinary factoring. If you carry out the expression enough, a pattern emerges. Each factor has an infinitesimal multiplied by a real number that increases as we increase the exponent and the number of factors. At the limit, where the limit is set as Aleph naught, we get the following terms. Using the algebraic expression set up between infinitesimals and infinites, we can simplify our expression by rearranging our factors in reverse so that all of the infinite exponential terms appear first in order. Since we have defined k0 raised to the power of Aleph naught equals k1, we can substitute k1 in. Since Aleph naught multiplied by k1 has been set equal to k0, we can substitute k0 for the factored term. We end up with 1 plus an infinite series of infinitesimals. Herein lies a predicament. Since we are treating infinitesimals and infinites with the same rules, adding infinitesimals together should not sum into anything more than an infinitesimal sum. However, we have defined Aleph naught multiplied by k0 equals 1. Using these definitions, we immediately run into two different possible solutions. Either the sum of a series of infinitesimals is infinitesimal, or the product of Aleph naught multiplied by k0 equals 1. In the first case, it's like Hilbert's paradox of the Grand Hotel.
Hilbert's Infinite Hotel. A grand hotel with an infinite number of rooms, and an infinite number of guests in those rooms. That was the idea of German mathematician David Hilbert. To challenge our ideas about infinity, he asked what happens if someone new comes along looking for a place to stay. Hilbert's answer is to make each guest shift along one room. The guest in room 1 moves to room 2 and so on. So the new guest would have a space in room 1. But what about when a coach containing an infinite number of new guests pulls up? Surely he can't accommodate all of them. Hilbert frees up an infinite number of rooms by asking the guests to move to the room number which is double their current one, leaving the infinitely many odd numbers free. Easy for the guest in room 1, not so easy for the man in room 8,600,597.
If we add the infinitesimals together, one at a time, the sum is still some infinitesimal. However, if Aleph naught and k0 are reciprocals, the product of Aleph naught multiplied by k0 equals 1. Even more problematic, if we run the summation in the ordinary direction, letting the finite exponentials appear first in order, we get the following. We assume that an infinitesimal raised to the power of some finite real number does not change the size of the infinitesimal. So Aleph naught multiplied by k0 raised to any finite power still equals 1. In this case, we get an infinite series of 1s, whereas a set, it has a cardinality of Aleph naught. These rules lead to three possible solutions. This may appear more than problematic, suggesting the abandonment of C3. However, by placing the possible solutions in order, we can argue that this particular algebraic treatment of infinites and infinitesimals gives us a range of values. This is definitely a radical choice. However, as peculiar as this may seem, the answer is stunning. 1 plus some infinitesimal raised to the power of some infinite, where the infinitesimal and infinite have a reciprocal relationship, yields a range of solutions that range from 1 plus some infinitesimal to some infinite whose value is the reciprocal of the initial infinitesimal. This becomes a new concept, perambulation. The range of solutions perambulates from a compressed form of the infinite or infinitesimal to an expanded form of the same, depending on how the hyperreal numbers are algebraically solved. A quick look at the expression Jacob Bernoulli used for deriving E, or Euler's number, reveals it has the same form as the expression used to derive perambulation. At a first glance, it appears that the concept of perambulation and Euler's number are incompatible. Two considerations. Bernoulli's expression has the solution E when n is a real number. Perambulation does not apply to real numbers, only hyperreal transfinite numbers, and E, 2.71 and so on, falls within the range of perambulation attributed to the same expression. Either way, perambulation and Euler's number are compatible.
Here's one that really is important. The number E, 1748, Euler. And you see it there in the middle of the page. He says, for the sake of brevity, we will use the letter E to stand for the number 2.7182818288459, which therefore denotes the base of the natural or hyperbolic logarithm. So Euler gave us E. The question is, what was Euler's influence on the calculus? For the sort of first-year calculus, yes, we sort of model our textbooks on his. But he never did the epsilon delta stuff, the analysis that you hit beyond calculus, that sort of limit-based calculus. Limits weren't around when Euler was working. He worked with infinitely small quantities in a kind of philosophical, metaphysical world that we now either don't like or we put it over in non-standard analysis.
If we go to section 1.7, perambulation, we can see these concepts expressed in an unconventional formal way. The expression for some infinite or infinitesimal perambulates over a range between a minimum term and a maximum term. In section 1.8, reciprocating perambulations, the reciprocal relationship between infinites and infinitesimals are modified to account for perambulation by extending the meaning of each infinite and infinitesimal term to have an expanded and compressed form. A closer examination shows Aleph naught can have a compressed and expanded form, making the distinction between infinite sets more intelligible and easier for ordering into a cardinal continuum. Here is a way to bypass the continuum hypothesis without contradicting the works of Gödel or Cohen.
Any consistent formal system F, within which a certain amount of elementary arithmetic can be carried out, is incomplete. In effect, there are statements of the language F which can neither be proved nor disproved in F. Basically, if the system is consistent, it cannot be complete. Imagine this is our system, ZCF, and we can prove axiom A, we can prove B, we can prove C. Eventually there's going to be some thing that we cannot prove either the truth or the falsehood of that needs to be a part of the system. We'll call that E. There might be some other system that could prove E, but inevitably there's going to be some thing that that system can't prove. Perhaps that the first system could prove. There may even be something that neither system could prove, which will bring us to Gödel's incompleteness theorem, part 2. For any consistent system F within which a certain amount of elementary arithmetic can be carried out, the consistency of F cannot be proved in F itself. So one of those statements that system F cannot prove is that system F is consistent. What that means is one of those statements that's outside the reach of our system is that that system is consistent. Whew! All right.
But one teenager didn't indulge in the normal pursuits of American adolescence. From a very early age, Paul Cohen was winning mathematical competitions and prizes. But he found it difficult at first to discover a field in mathematics where he could really make his mark. Until he read about Cantor's continuum hypothesis. It had foiled all attempts to solve it since Hilbert made it his first problem way back in 1900. With the arrogance of youth, the 22-year-old Paul Cohen decided that he could do it. Cohen came back a year later with the extraordinary discovery there was one mathematics where the continuum hypothesis could be assumed to be true. There wasn't a set between the whole numbers and the infinitesimals. But there was an equally consistent mathematics where the continuum hypothesis could be assumed to be false. Here, there was a set between the whole numbers and the infinitesimals. But his method was so new that nobody was absolutely sure. There was only one person whose opinion everybody trusted.
He had to come and make a trip here to the institute right here to visit Gödel, and it was only after Gödel gave his stamp of approval in quite an unusual way by said, give me your paper, and then on Monday he put it back in the boxes saying, yes, it's correct. Then, of course, everything changed.
We have maintained that the power set of Aleph naught is Aleph 1, and we have not contradicted whether or not Aleph 1 is the cardinal number of the set of all real numbers. However, we have expanded the continuum to include hyperreal transfinite numbers, a continuum different from Cantor's. Limitations placed on the traditional continuum hypothesis do not necessarily apply here. We can deduce a cardinal continuum with infinite degrees of infinity, where the power set of Aleph naught is Aleph 1, where there exists no other degrees of infinity between Aleph naught and Aleph 1. Aleph 1 is the set of all real numbers, and the power set of Aleph 1 is not the continuum, but the next cardinal number. Appealing to the idea of a cardinal continuum with infinite degrees of infinity, we can imagine some greatest set, least its power set, where this power set is the continuum. Though slightly different from the traditional continuum hypothesis, the question becomes, what is the cardinality of the continuum, if not Aleph 1? Section 1.9, Arithmetical Treatments of Perambulation, applies the compressed and expanded forms of perambulation to exponentiation of both infinites and infinitesimals, and how they have been treated algebraically. Notice that the mean solution and the exponential treatment thereof gives us a peculiar equivalence. We can set up two sequences of inequalities with the mean solution representing an interesting cutoff, the number 2. Section 1.10, Subambulation, and Section 1.11, Ambulation, discuss further bifurcations of perambulation, which eventually lead to 1.15, counting the continuum using power sets. Though the continuum is uncountable, perambulation allows us to sequence uncountable sets into a consecutive order. This consecutive order, which is beyond countability, is some form of superorder captured by the range of solutions denoted as perambulation. A closer look at counting the continuum using power sets reveals a margin by which a particular counting of the continuum can be performed. If we simply apply the appropriate reciprocal exponent to both sides of the equation, it reveals a margin identical to the mean solution of perambulation, the number 2. Alternatively, if we subtract 1 from both sides, it reveals a process for iteration.
In his book, Mandelbrot said that many forms in nature can be described mathematically as fractals. He said that you can create a fractal by taking a smooth-looking shape and breaking it into pieces over and over again. Computers made it easy for Mandelbrot to do iteration.
That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula. Get another number out, and you keep iterating that over and over again.
The series of numbers you get is called a set, the Julia set. At IBM, Mandelbrot did something Julia could never do. Use a computer to run the equations millions of times. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
So here's sort of just the naive definition. What happens when I take 0 and I plug it into this function, and then I keep doing that to the result? Now, what the Mandelbrot set is concerned with is what happens to the size of these numbers. So it turns out there's two options. The first option is that the distance from 0 of the sequence we get gets arbitrarily large. f1 of 0 is equal to 0 plus 1, which is 1. f1 of 1, this is 1 plus 1, which is 2. f1 of the previous thing, which was 2, is 2 squared plus 1, which is 5. f1 of 5 is 5 squared plus 1, which is 26, and so on. So this is what people mean when they say that the iterates go to infinity. The other thing that can happen is that the distance is bounded, the size is bounded. And in fact, you can say that it never gets larger than 2. So you have this sort of dichotomy where only one of two things can happen. If you give me a complex number c, and I start iterating 0 under that function, either the distance of the iterates to 0 gets really large for all of them, or it stays close to 0 within 2 of 0.
An infinitesimal raised to the power of the corresponding infinite produces a next infinitesimal. Each consecutive iteration proceeds towards expressing a section of the continuum, with a minimum range of 1 plus k sub n less than 2, and a maximum range of 2 less than infinity, and a median value of 2.
But there's another possibility, so let's look at, well, a good contrast maybe would be z squared minus 1. f minus 1 of 0, that's 0 minus 1, which is minus 1. If we plug in minus 1 to that function, we have minus 1 squared, which is 1, which is 0. Oh, wait, okay, but we know what happens to 0, right? It goes back to minus 1. So these iterates just alternate between minus 1 and 0, and so in particular, they never get large, right? So that's an example of case 2. The definition of the Mandelbrot set, M, is the set of complex numbers, C, for which case 2 holds. Case 2. This is also, in case you're curious, how these pictures are always generated. Everything that's in the Mandelbrot set has to be within distance 2 of the center, right? Because of exactly this case 2 thing that I said, that once your iterate is larger than 2, you're out of the picture. So the inside of this thing, let's fill this in here. This is what's known as the Mandelbrot set.
What's happening at the edges then? Is that where things are interesting?
That's where things are interesting, right? Where you go from blowing up to not blowing up.
But when the Mandelbrot set was first published, mathematicians, for the most part, reacted with scorn.
In the Mathematical Intelligencer, which is a gossip sheet for professional mathematicians, there were article after article saying he wasn't a mathematician, he was a bad mathematician, it's not mathematics, fractal geometry is worthless. His colleagues, especially the really good ones, pure mathematicians that he respected, they turned against him.
Because, you know, you get used to the world that you've created and that you live in, and mathematicians had become very used to this world of smooth curves that they could do things with.
They were clinging to the old paradigm, when Mandelbrot and a few people were way out there bringing in the new paradigm. And he used to call me up on the telephone late at night because he was bothered and we'd talk about it. Mandelbrot was saying, this is a branch of geometry just like Euclid. It offended them. They said, no, this is an artifact of your stupid computing machine.
Is the cutoff in perambulation and the margin found in counting the continuum somehow related to the boundary found in the Mandelbrot set? We know that each successive term is bigger than the last, and adding infinitesimals does not generate larger quantities. On the other hand, it can be deduced that raising some infinitesimal to the power of some infinite generates a smaller infinitesimal. Presuming that this can be used to establish distinctions between infinitesimals, a series of terms can be sequenced as inequalities. If we subtract 1 from each term of the sequence, we get the following sequence of inequalities. If we duplicate this sequence of inequalities and add both sequences together, but shift an entire sequence by 1 term, we get the following sequence. Focusing in on the middle terms, we see that we have inadvertently isolated the number 2 between a minimum and maximum solution. We should label the maximum solution greater than 2 as element A, and the minimum solution less than 2 as element B. The number 2 is a unique number such that element A contains every element greater than 2, real or hyperreal, and element B contains every element less than 2, real or hyperreal. In doing so, we have generated a quasi-Dedekind cut, but instead of using rational numbers to produce a unique irrational number, we are using hyperreal numbers to produce a unique real number, the number 2. Whenever, then, we have to do with a cut produced by no rational number, we create a new irrational number, which we regard as completely defined by this cut. From now on, therefore, to every definite cut there corresponds a definite rational or irrational number. It can be demonstrated using the expressions from C3 that hyperreal transfinite numbers exist along the continuum, assuming that the continuum is greater than the set of all real numbers. Furthermore, if we use the negative expression of hyperreal numbers over the continuum, bringing C3 into the complex plane, the sequence of inequalities can be used to demonstrate the hyperreals over the Mandelbrot set. Interestingly, the number 2 is excluded, yet the maximum and minimum solutions iterate towards and away from the number 2. If we zoom in the Mandelbrot set, I think we can actually see why. Referring back to the questions found on page 36, does this evidence that the sequence found in the section 1.15, counting the continuum, is truly infinite?
I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, and no matter how much we magnified it, 1,000,000 times, 1,000,000,000 times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier of the M set is infinitely complex. Most people, when they say infinitely, they mean only or rather big, but this is really infinity.
As crazy as it might be, C3 may be giving us new insight into the bizarre reality of infinity. Finally, if we're going to let a sequence of infinitesimals, whose values sequentially approach 0, and let those infinitesimals be reciprocals for an infinite sequence of infinites, whose values sequentially approach the cardinality of the continuum, 2 pressing issues must be dealt with. 1. If 0 is at one extreme of the continuum, then what is at the other? In other words, what is the reciprocal of 0? 2. Whatever the reciprocal of 0 is, it cannot succumb to Russell's paradox. The cardinality of the continuum cannot be the set of all sets.
The set of all sets that are not members of themselves. Is this set a member of itself? If the set is a member of itself, then it is not the set of all sets that are not members of themselves. Why? Because one of the sets that's included, namely the set itself, is a member of itself. However, if it's not a member of itself, then it's not the set of all sets that are not members of themselves. Why? Because there's one set out there that's not a member of itself that's not included, namely, once again, the set itself. the set of all sets that are not members of themselves, and that set is both a member of itself and not a member of itself. This was a problem for set theory, and therefore it was a problem for math.
These issues become apparent once the reciprocal relationship between infinites and infinitesimals is plotted along the continuum.
Around 1500 years ago, or a little longer if you're watching a repeat of this program, someone came up with a stupendous, incredible, extraordinary idea. They invented an entirely new number. And it's in here, inside this tiny 1100-year-old temple in Gwalior, northern India. Once invented, it transformed the life of one in a way that would eventually change the entire world. Well, here we are. The first undisputed example of India's greatest invention. The new number. The holy grail of numbers. 0. Well, you might say, what's all the fuss about? I mean, what's so wonderful about inventing a symbol that means nothing? Well, a 0 on its own would be nothing, well, obviously. But when you teamed 0 up with 1, magic started to happen. And when they were joined by the rest of the troupe, the results were spectacular. With just 10 digits, the Indians could make numbers infinitely large, as well as infinitely small.
Question. What if 0 itself somehow is at both ends of the continuum? What if the relationship between 0 and infinity, nothing and everything, have an underlying commonality? The image of the function 1 over x wrapping around an infinitely closed Cartesian coordinate system comes to mind, where the function becomes continuous over 0 in a very peculiar way. This shouldn't be considered just some pretty picture, but insight into the relationship between 0, infinity, and infinitesimals. As crazy, bizarre, or even ridiculous it may seem, it is very convenient to have 0 at both ends of the continuum. Though the idea of a greatest possible set succumbs to Russell's paradox, ironically, 0 doesn't appear to have this problem. If 0 is considered to be both the empty set and the set of all sets, to ask if it is a member of itself becomes a very meaningless question. Now the naysayers are obviously going to jump all over this, hyper-focusing on the problem of defining 1 over 0. The killer critics are also going to jump all over the fact that you can derive any number from 1 over 0 if you try to use it. They will say that this is meaningless nonsense. Well, I'm saying that I can sequence this nonsense into a set of unordinals, the nonsensicals. I can use this nonsense and generate a union between both the ordinals and these ridiculous unordinal rejects. Using a Cantor-style diagonal, it can be demonstrated that this set has the same cardinality of the original set of all ordinals, despite the extra nonsense. Therefore, though 1 over 0 can be used to generate nonsensicals, and despite that nonsensicals can be ordered, nonsensicals do not have a higher cardinality than the set which contains no nonsense. We can order the equations that use 0 algebraically to derive any number, suggesting that 0, in some bizarre way, is the continuum, symbolically. The idea that the continuum could be expressed as an infinite circle is evocative. 0 would be both the smallest and the greatest. It would be nothing, yet everything spread out over a continuum of all possible numbers. Or something like that. Just a notion.